Okay, awesome. Okay, cool. So we're gonna learn some lean. So the first comment is that you need to, when you open lean, it would be nice, read this question on a Stack Overflow, how to create a lean project that works. But the TLDR is that we can create I can create a video for that one later separately. But what you need to do is like where you initialized your lean, you need to open that file directly on VS Code, basically. So that is what I have now. And you can see I've installed MathLib, everything is here. We can do a video for that separately later. Right now, we'll jump into the lean stuff. So, yeah, let's do it here. So as you can see, I've started making notes on tactics and things like that. You can add stuff to those if you want. Yeah, so we're gonna learn. I think the natural numbers game is like the famous way to do this in Lean, but I'm just gonna do it from scratch, doing something else, using my own way to prove natural number stuff. It's gonna be very simple, probably more simpler than what they have there, but I think it will introduce concepts like inductive types and constructors. So which is like very important for Lean and induction. So let's call it basic nets. Cool. Okay, so this is a comment. So the first thing is an inductive type. So in Lean, everything is a type. I mean, I think official great type theorists will kill me for saying this, but I personally think of types like similar to sets. It's not exactly the same. I forget, there was a good example of what is a difference. I think like sets, let's see. Yeah, I can't remember, but inductive types are like functions sort of to create objects. But so for example, look at this. So Lean doesn't really know anything. So it doesn't know what natural numbers are. So I'm gonna just create one. Inductive. I'm just gonna call it a nat. Like it's gonna be unary. And I'm gonna call it nat, and it's gonna be of type. So I'm creating a natural number, and it's already off the bat starting to suggest things. So I'm gonna create basically a constructor, which is a function that creates objects. 0 and successor. So natural number. So that's how you define natural numbers. And then I'm gonna check the type of unary nets. Actually, I'm gonna undo this. I think the standard way to define nets in Lean is to do camel, like camel case, unary net, type, 0 unary net, successor. And what this does is, for example, to create, so like 1, 0 is just 0, like this. Okay, yeah, I knew this would happen because I already did this exercise for myself. But basically, it has no function to print things, so I need to tell it to do that. So I think it's reproducing repr or something. So create repr function. Let's see. Okay, no, it's not doing it. So I think it's deriving. No. Yes, Copilot is not very good for Lean. Okay, didn't really do this, but okay, so this should work now. So now it worked. So eval, like bang eval, basically it's a way to just check that 0 works. And if you notice, I need to tell it which type and which constructor I need. And here on the Lean board, it just displayed that value, right? Okay, so now eval unary. I'm sorry, I'm gonna now create the number 1. 1. This is how you create 1. And it's just gonna be successor 0. And the way you create 2 is successor 0. And this is why it's called unary. Yeah, does that sort of make sense? Any questions so far? Actually, one important thing is to check the type. So let's check this is a useful function. So what do you think unary nat? So check unary nat. What do you think this will give you? Yeah, because it's of type, basically. Nice. And what about unary not zero? Yes. And what about the other one?
Also unary net?
Unary, so the successor one.
Yeah.
It should also
be
be
a
unary
unary.
net.
And what about successor zero? What is the type of this?
Should also be
Yeah.
unary net.
Yes, exactly. Perfect. Excellent. Okay, cool. So now, because I don't want to write unary net all the time, I'm just going to say open. Okay, or let's see if Copilot can do it. Open the allow. Oh, there it is. The for unary net. Oh, okay. Let's see if it does it. Okay. Now just a sanity check. Oh, I sometimes do things like that because of Python. Yeah, great, great. It did it. Awesome. And here on the right, we have everything. Cool. Okay, now what we want to do is first is to define functions, and I'll show you two ways to define functions. But it doesn't know, we haven't defined anything for nat, so it shouldn't behave like nats because nothing has been defined. So let's define addition. So we do add, and there's a nice, like Copilot is already telling us, but there's a way to define functions such that you don't even need arguments, which is sort of like interesting. So here it is. This is the functions. Oh, I think this shouldn't work. Yes, I knew this wouldn't work. Yes, this is not correct. MN. Okay, so this just means, okay, oh, it doesn't like it. Missing case. Yes, I know that. Okay, so it's already complaint. M, A, B, C, D, G, H, I, J, K, L, M, N. Yes, okay, cool. So what I'm doing is addition. How is addition defined? You have addition is just a function, takes two natural numbers and it adds things. And what it should, when it's 0 and 1, should return n. And when it's not 0 and 1, look at how it like opens up the banana or the onion peel. It basically opens up the first argument because it's success. Because if it's not 0, then the first argument should be a successor, right? So this is what it's inductive recursive types. I think that's how I think about it. So successor m, then we do successor add mn. Basically, you have a successor, you extract that, apply it at the end, this constructor, and then keep adding and finish. Actually, I'm going to do prime here, and you'll see why in a second. And that's the way we define addition. Yeah.
So right here you have unary not pointing to unary not pointing to unary not.
Yes.
Is that saying that you take in two unary nats as your, I guess, like input to the function, and then you output a unary net? Is
No.
that how? What is the?
But that's a great question. What it means is that it receives a unary net, and it returns a function of unary net to unary net, because there's something called binding. So the arrow, the function arrow, binds to their right. So it actually takes a unary net and returns a function of unary net to unary net. So that's automatically.
Oh, so is it like you add 3 and 5, and then when you do add 3, that's a function that outputs, like, if you plug in A, it outputs A plus 3.
Yeah. It applies partial functions, I guess. Yeah. So, okay, that's a great question. Actually, let's make sure Brando is not making things up. So let's check the type of add. Actually, before we do that, I'm gonna do something that might be weird, but I'm gonna rename our function to be called add left. And the question is like, why is Brando doing that? Well, the thing is that our function is actually adding, but recursing on the left side. Because we could have added right and recursed on the right side, and that is actually going to change our proofs. In this, you'll see, we're going to do induction and reverse depending on where we define add.
Assume commutativity.
Excuse me, could I borrow the remote controller for TV? In this room, there is no controller. I'm sorry. Sorry to interrupt.
So, yeah, what were we saying?
Left, right.
Oh yeah, you'll see how that defines, how that affects the proofs.
Okay.
You will do the induction on the left side or the right side, depending on how we define add or left. Okay, I'm just gonna do, okay, let's just make sure, okay, that add left is what we think it is. I'm just gonna do 0, and let's see what it is. Okay, it is a unary net to unary net, right? Just as we expected. And add left successor. Okay. Okay, sure. Let's just see that it, oh, okay, we don't need to do that. So I'm just gonna, okay, cool. That's basically it for that question, right? So now let's just evaluate it. And let's do add left 0, 0. It should return 0. And it did. Now let's just try successor 0. Let's do 0 successor. Let's do 0, 1 should return 1, right? According to our definition. Now let's do 1, 0, and it should return 1 still because it, cool, it works.
Yay.
Okay, so now that it works, let's just define, I'm just gonna define add right, but this time I'm gonna use parameters. So parameters are like in the declaration, the name of the variables basically. And arguments are like what you call into a application of a function. So add right, mn, and unary net. Oh, okay, yeah, okay, it tried doing that because we already defined it. Okay, so what I'm gonna explain what this means. It's saying you're defining a function, it takes m and n, now they're explicit, and it returns, this is the return type, unary net. And then you need to say colon equals to say what the content of that function is. Let's see if I remember the syntax. Will this work? Let's see if it works. No, yeah, it doesn't like it. Sometimes I'm okay. So either me and Lean 3 and Copilot don't remember the syntax. So okay. So what I'm gonna do is gonna cheat and see my cheat sheet here. Okay. I guess that's what it wants. Yeah. Okay. I'm just gonna do that then. So I'm just gonna do something called a match statement. I'm just gonna match add right. So I'm gonna do it on the left now. And it's going to be 0. If it's 0, return. If the right one is 0, then return the first argument. Otherwise, if there's a successor, there's only 2 cases. Match. I think the match statement, if you remember previously, it got mad that we didn't take care of all the constructors. So now I did the same thing basically, where the right one could be a successor. So I peel it out, put it on the front, and keep recursing. Does that make sense?
So the match statement is kind of like a case or like a switch for the value of n.
Yes.
So
But it match, but it deconstruct. I don't know if this is the right word, but it deconstructs the cases by your inductive type. So there's only 2 constructors, 0 and successor. So there's only 2 things inside of the constructor function that could be happening. 0 is a constant, so there's nothing to extract. That's why there's no argument. But successor is like pulling it out. And one comment that I don't know, I think this is true. The Lean syntax for functions, if you look at the first one with just types, with like without the arguments, sorry, the parameters, I mean, without the parameters being explicit, it looks like equations. Like it's a rewrite rule. You have this symbol and it rewrites to this symbol. And that's sort of nicer in the sense that this looks like more like functional programming. This looks more like mathematics.
Are they equivalent?
Yes, I think
you have written add right with that sort of syntax?
Yeah, we can actually, that's what Copilot was trying to force me to do.
Okay.
Like we can just okay, now it's inferring that I want to test it. That's a good yeah, and it works as I would expect. Yeah. I think like a nice exercise could be, I'm going to write it. Maybe you guys can have fun with this, is to prove that add right is equal, like it's equal to add left. I think that could be for all inputs. That could be like a nice exercise. But because I haven't tried it before today, I'm not going to try it because I don't want to make a mistake and embarrass myself. But yeah, let's see. Cool. Okay, now Lean is a language for math. So let's make all of this look like math. This doesn't look like math. So let's do something called an infix notation for this. Oh, it already told me that it wants this. Okay, so I'm going to just focus on add left. And what this means is now eval of 0 plus 0 is just add 0. Yeah.
Wait, what is infix 65? What is 65?
There's some rules about how binding and things like that work. I don't remember what that means. We would have to look it up. So right now, this works as I want it, but the main point is just to show you that now I can change the binary operation, the function, to just use like normal math notation, basically,
Okay.
like with an infix, basically. I think infix L might be it's binding to the left. I wonder if binding to the right, yeah, that does work. So that's probably what it's doing, like how it's
Okay.
putting the parentheses,
Mhm.
because this is actually equal to, add 0, 0, right?
Yeah.
Right? That's what this is.
Mhm.
And actually, just as an interesting comment, like when you do, so associativity, actually, associativity is not a thing that comes for free. If you have A plus B plus C, like how does this work actually, right? Like this could be two functions, applications. It could be add A, B, C, add, or add, yeah. If you think about programming, like there's no reason, even if the name is the same, that these two things should return the same thing. This is
Mhm.
like a very special property of addition, right?
Mhm.
So these are things we can prove. I don't know if I'll prove it today, but I don't think I have time, but yeah.
Wait, in the definition of like add left and add right,
Yeah.
it's because our unary nat type is inductive that we get commutativity, right?
Yes,
Okay.
that is inductive. Well, everything's in, I think it's because of the combination of two things, how we define add and how we define unary nat.
Okay.
Because there's a lot, I can define arbitrary inductive types, and I'm sure I can construct one so that there's some function that isn't commuted, like associative
Yeah.
or a commutative. Actually, this is associativity.
Yeah.
So it's a property of addition.
Okay.
Like it's because addition works this way. We can go into more depth about it. I think that's not as important as like induction. Like
Mhm.
that's what I really wanted to show you
Okay.
guys. And then, okay, so now I just want to show you how, okay, now that we've defined all this, I'm just going to define, let's see if I remember how to do this, but I'm going to define a theorem. And I'm going to just say, add 0 is 0. Let's see if I know how to do this. So we're just going to do add left. Actually, we're just going to do 0, 0. Okay, 0 plus 0 equals 0. That should be true, and that should be true just by simplifying 0.
Uh-huh.
So this is a tactic, and it just applies addition basically and simplifies it and compare. It does a couple things. It unfolds our addition definition, then it just compares that the equality holds, and it finishes.
Wait, so why don't we need a by here?
Yes, we can talk about that in a second. But the reason is that I'm pretty sure this is correct, but theorems are, how do you say this correctly? Theorems and function definitions are similar in the sense that a theorem defines a type, and the proof of it is is a program that has that type. That is something called the Curry-Howard homomorphism correspondence. I forgot the name right now, but it basically shows that isomorphism, that's a word. So if you notice, colon equal is like the notation for functions that we defined here in the match thing, in our definition in add right. So this actually creates, I wonder if this will work. This actually creates, no, not info. Okay, I don't know. I know that it works in, maybe we'll find a proof where I can do this. I've done this before, but you can print the proof term. Like tactics build proof terms. So when you say colon equals, you can just define the function actually, and it proves the theorem. Tactics instead, actually, what they do, by gets it into, as far as I understand, we can look it up, but gets it into tactic mode and starts interactively building a proof term for us, a witness that the proof is correct.
So by is like we're building the function itself.
Yes.
Whereas like just without the by is we already have the function, we can just plug it in.
Yes.
Okay.
Mhm.
Yeah.
What does RFL stand for? Is it just-
Refl, it's reflexivity. If you think about what's the word in equality, total ordering? If you've seen things like that, reflexivity is like one of those Cartesian products, right? That like what type, like the diagonal, right? Like you're saying like these two things correspond,
Oh,
right?
okay.
And like less than is like the lower part
Uh-huh.
and greater than is
Okay.
the upper part. Yeah, things like that. And equality is sort of complicated in lean, actually. There's things like definitional equality, et cetera, et cetera. I don't remember everything right now, but when it becomes relevant in your proof, you can always look it up.
Uh-huh.
Cool, great questions. Anyway, let's try. I think that's a good, so this would be more or less debugging things I would do when I develop. I would develop a definition. I would check the type is right, that evaluates if there's an way to evaluate it, to make sure it evaluates the right number. Write a simple theorem about it. You'll discover that when you try to do things like that, but for real numbers and you try to evaluate them, they're not really evaluatable. So eval won't work. We'll check that out later, but these are, you can still do theorems about them to debug, to do unit tests. Lean's, in my opinion, is still like a programming language, so you should debug.
Okay.
Yes.
You should have good programming language practices, like programming practices, which is like having unit tests. So we're going to prove two more theorems, and it's going to be really simple, and you'll get a good sense of lean. So the first one is we're going to do it only on add left. That's the one that has the infix notation. So implicitly, that's just the one we're focusing on. But it's recursing on the left. Therefore, 0 plus n should just require a rewrite rule, right? So let's try that theorem.
Wait, should that equal n or 0?
Oh shit. I mean, oops. I mean, 0 plus or add plus n equals, and I'm trying to use the like naming notations that I think are common in Lean. I'm also learning that as I'm going, so hopefully this is like a good naming. So there's two ways to prove this theorem. Lean is suggesting me something I think is gonna work.
Yeah.
Yeah, this worked. Okay, so okay, let's try to do the math one and then the programming languages proof. Okay, yeah. Okay, so Copilot is gonna start suggesting things according to the character I give and predict the next thing. Since I haven't done anything, it's sort of predicting, I think, the most common one. But for explanation purposes, I'm gonna define the name of the theorem and now the return type immediately.
Okay.
So the return type should be, oh, interesting. No, this is not gonna work. Oh, it works? No, it doesn't work. I knew it wouldn't work. Okay. Anyway, this is the function we're trying to define, right? Basically, for all natural numbers, 0 plus n equals n. So how do we prove this? This is what I'm trying to prove. So I'm gonna start my tactic mode. And now the first thing I'm gonna do is the intro tactic on n. There's only one variable. So what that does is it basically, so before I did the intro, look at the top right, we have a goal. So the goal is to prove that symbol, basically, that expression. So also it's I think Lean always gets mad if you don't have a sorry or things like that. So I'm just ignoring that. Obviously, we know the proof is not done, so I'm just ignoring that we are not done. So the goal is this, right? But we need to like, so if you have a proof and you say for all some property holds, you say consider some n. So let's consider some n. And now it's like in the left part of the bar. So the left part of the bar is like all your assumptions. I think in programming languages, they call it typing environment. For us, it's like our assumptions. Our assumptions is n is a unary nat.
Okay. Wait, so the intro thing is like, you say like let n be any natural number. That's
basically
equivalence to.
Yeah.
Okay.
Yeah.
Like fixing the value for n so we can.
Yes, it's sort of fixing any value for n.
Like an arbitrary.
An arbitrary one. Yeah, correct. Yeah, that's right. And then it's saying that and the goal now became 0 plus n equals n. which sort of makes sense. So now intuitively, we know we only need to like do the simplification. I think Lean has more automation than Coq and Isabel. So I think if I do simp, does it let me do it?
I think R.
Oh, it doesn't like simp. Oh, cool. Simp, and it add left. Oh, cool, it worked. So that worked.
Wait, I tried it and RFL also.
Yeah, I think it does. I knew that would work too.
Yeah.
But
Does so RFL is the same thing as
reflexivity.
yeah.
So I think actually this is a good time. Let's do this. I'm gonna comment that out. I'm gonna write REFL and I'm gonna hover over it. REFL tries to close the current goal using reflexivity. This is supported to be an extensible tactic, and users can add their own support for new reflexivity relations. I don't know exactly in this context what extensible tactic means, but I know that extensible programming languages means that as you program the language, you can define new constructs. So like, just like we did like def, we can define, at least in Coq you could do it. You could do def2, and then it's a new keyword sort of thing. So I think this is sort of similar. You can like extend tactic for reflexivity and do magic.
Oh, so like kind of like overloading the tactic with like your own.
I think, I mean, also like interactive theorem provers have their own tactic language. So we can probably implement our own extended tactic basically by programming, because it's automating things so that it's easier for us to work with. Anyway, that's not all I wanted to show. If you command or maybe control, I think we're all Macs, but I think if you do command click, or it even shows you like macro, I forget what macro means. Oh, cool. It shows you different things if you hover and command.
Oh, whoa.
So it says, oh, I think REFL does tactic and equality REFL. So anyway, what I wanted to show is that if you click on it, it will look, we now are inside Lean. Mathlib, I think. So the tactic.lean file, I'm gonna remove this and I'm gonna go into it again. Yeah. Basically, this is like tricks for developing better, being a better developer. You can look at the implementation itself and then see if that's what you need to progress in your proof. If is that the right tactic or is that the right theorem? We will try to inspect theorems too. But let's see, intro. Let's just go into intro. Hover. Let's just sort of hover and see what it says. Introduces one or more hypotheses, optionally naming and or pattern matching them. For example, for each hypothesis to be introduced, yeah, like basically you can just hover over whatever you want. I wonder if theorem lets me hover over it. Okay, fine. Theorem doesn't. I wonder if it lets us. Oh, open. It's this finding open. Makes names. Okay. What about if I hover? Yeah. Anyway, that's it for that. Ready? I'm going to show you one trick for being better developers.
Did you click in the intro? I didn't.
Oh, I didn't click. Oh, it's not letting me click into the intro.
Click into it. I think it might just be for R.
No, I don't know all of Lean perfectly yet. I don't know if this is a bug. But anyway, whenever you can click into it, click into it.
Yeah.
But I was going to show you a trick for developing because it's hard to find all the things you need, right? So sometimes you can do simp, question mark. Oh, unknown tactic. Okay, didn't like this. Simp, question mark, made no progress, unknown tactic. Darn. Okay, what about rewrite? No. Oh, actually, I'm curious. Does rewrite at left work? Yeah, it also works. So rewrite, okay, I know how rewrite works better than simp, but you can also hover into it. But rewrite, that's because of the Lean manual for theorem proving. Rewrite has an equality or like the if and only if or the equality, and it rewrites the first term from left to right. So if you wanted to work the other way, you want to use the equality in the reverse direction, you need to do this arrow. And it shouldn't close the goal now because it can't rewrite, it can't rewrite it in reverse because it doesn't know how to, there's nothing to, it can't rewrite this to n because there's nothing that matches on the right. But on the left, there is this matches, right? That's what, so it's trying to do the addition in reverse. I told it on purpose. Yeah,
Wait, so the way rewrite
on the goal, it tries to rewrite the goal.
Uh-huh.
And if you say add H, that will actually rewrite a hypothesis if you have a hypothesis with that name. So you tell it what to rewrite and in what order and in what direction.
Okay. Wait, so how rewrite works is it tries to match the goal you currently have with something inside of the theorem that you're giving it, or like the operation you're giving it.
I think so, something like that. I think it's rewrite works by having the term or the theorem that you're giving in the brackets and has it unify with the goal.
Okay.
The first term that unifies. What that means is that the shapes look, there's an algorithm called unification. It tries to use that to find matches. And if they match, then it uses it to do the rewrite.
So in this case, we're trying to match 0 plus n with something in the definition for add left.
Yes.
And then it found add left, or 0 n goes to n, and then it matches that together, and then it shows that n equals n by.
Yes.
Yeah.
Correct.
Okay.
Yeah. Right. That is it. So now the proof is done. I wonder, can we print the proof term? Yes, no? Let us.
Gives an error.
It still doesn't let me do this. I can't remember how I did it. So did I do a print here? Oh, I know there's a way to print the proof terms. Sorry, guys, I can't remember the syntax. But maybe I wonder, well, Copilot. Okay, so I'm gonna remove this because like the reality is that a simple theorem like this is probably gonna be close by reflexivity because it's very simple. But I'm gonna do a last check and last attempt and tell Copilot to give me the proof term. Print the proof term for me, please. Oh, I see. I need to give the name of the theorem. Okay, cool. So actually, you can even see the tactics that it did. So so fun n is actually, there's an equivalence between proving and programming. So if you think about it, if you say for any n, functions have to work for any n, right? So that's what that's doing. It's saying you said intro because you're considering some n. So the function that you have to define has to be an abstraction with n. Does that make sense?
Yeah.
Like the function has to work for any n. So define a lambda function. Like it's just basically an anonymous function. It's a function without a name. And the variable is n. That's it.
So it just takes an n and then it works.
It takes an n and does something. What does it do? Well, it does this equal refl thing. And that's just how refl figured out what you had to do with the definition of addition, and it made it into a proof term that has the type of the theorem that we want. Yeah, so that's it. So that is cool. Thank you, Copilot. I'm gonna move on so that we do everything. So now the next one, n plus 0 equals n. So this one's slightly more complicated and requires proof by induction. So we're gonna try to prove, actually just, okay, this is, now that you know how to do proofs, we can do the proof again. And instead, we're going to do it in function notation. This is immediately basically does intros for us because we're putting the intro as a function abstraction already. So now it just did it in one line. So I just wanted to show you that. And I assume that the print is going to work. The printing of the proof term, the elaboration. Yeah, it worked. Great. Awesome. Okay, now the inductive version of the proof. So now we can guess just intuitively, look at the definition. Successor, this doesn't sort of simplify, right? Like these recurses. So how do we recurse in a proof is the question. And the way we recurse, if you think what recursion means, is like you assume it works for everything below. So that's what induction is.
Yeah.
Assume it works for everything below. In computation, you just keep going down. In the proof, you just sort of assume it and change the expression. That's what induction sort of is.
Yeah.
So let's try it. Theorem, N add N equals N. I'm gonna just keep the math notation.
Wait, should it be?
And add 0.
Oh,
Yeah.
N add 0, sorry. 0. I'm just gonna let it complete this. Okay, it did everything in one go. So intro N again. Okay, so before we do intro N, we know that we have a for all, so we need to say for some N. Now we have the goal that we want to prove, and we need to do something. So because we know that the function recurses and it's an inductive type, a good candidate is to induct on the constructors. There's two constructors, 0 and successor. So that's what we're going to do, induct an N. So we're going to tell it to inspect basically both cases. So the first case, I wonder if we can do dot. Is this where the dot works?
Okay, so these are the separate cases. But why
Yeah.
did the
Oh, okay. This is
Copilot put in bars, didn't it? So is there like any significant difference between the two?
yeah, I know. I'm just let me just experiment. Oh, it
Okay.
didn't let me do it. Why didn't it do it? Huh. Oh, I think it might it be like the indentation? Okay, this is me exploring Copilot. Sorry, Lean. Okay, stop it. Okay, I'm just gonna let it. Okay, there's two cases, right?
Mhm.
0, when n is 0, what is it? When n is 0, let's see, 0, what do we have? The proof is now 0 plus, it's the base case, 0 plus 0 equals 0. We already sort of know that's gonna just be pretty easy. It's just gonna be REFL, right?
Yeah.
Could we
Cool.
also similarly use our theorem from above?
I think so.
0
Let's
is
try
0?
it. I don't, I think, I don't know if it's apply 0.
0 is 0.
Oh, alternatives, no goal. I wonder, does that work? I think that worked. Yeah,
Oh,
Yeah,
okay.
it works.
Oh, okay.
yeah, it worked. But this one, I think it's simpler to just use REFL.
Yeah, yeah.
Uh-huh.
We
When
can,
do you put apply and when do you not apply?
okay, those are like specific tactics that we won't have time to
Okay,
go
okay.
into today.
Yeah.
But because there's like 3 tactics that I can't remember right now the difference, which is rewrite,
Mhm.
simp, apply, and other and
Exact.
exact, I think, is for giving the proof term. But
Mhm.
anyway, I think we can discuss those once they're a problem. For now,
Mhm.
this is good enough.
Okay.
And Brendo has to remember all the things he learned in the past for FM. So, okay, what is the next case is intuitively, we will have an induction hypothesis that we get for free.
Mhm.
And the other case is successor, right? The
Mhm.
successor is the other case for n plus 0. So now look at it. Our initial goal was n plus 0 equals n. So n could be 0 or successor n, right?
Mhm.
So that's what we did here. If you look at our goal, now we have successor n plus 0 equals successor n.
Mhm.
So now,
So you're writing n equals successor n prime, and you're assuming the hypothesis for n prime and showing that it works for n.
yeah, basically, what we now just need to show is this, the final goal, successor n prime plus 0 equals successor n prime, given these facts.
So the induction, the IH stands for induction hypothesis. right?
Yeah, we named it. I wrote it,
Oh,
right?
okay.
I named it. Copilot helped me remember the syntax, but I named it.
So you can name IH anything you want.
Yeah.
It's not like a.
Yeah, it's now H.
Okay.
Yeah. And n prime is like a name I named. Okay, so let's see if I can do the proof by steps so that it's not like magic. What I would do first is just sort of unfold the definition of add on the left
Mhm.
and rewrite it. So let's rewrite it according to add left. Okay, cool. Look, do you see how the goal transformed?
Mhm.
Do you see that to Emily?
Yes, yes.
And I'm gonna tell it, that's all I want you to do. So out, let's see, if you notice the inside is the induction hypothesis.
Mhm.
So if I do rewrite induction hypothesis, it should plug in n prime.
Oh.
So let's see if it does it. Oh, it also solved it. Okay, so because the automation is so powerful, I think it just, oh, okay. Oh, cool. Did you see? Now it's successor n prime
Yeah.
equals successor n prime. Now we close the proof and we're done. We did our
Wow.
first proof by induction. Let's see. Does that any questions? Actually, there's a way to rewrite this. I'm just gonna rewrite it so that it's less, so that I think this is the proof we would actually find in MATLib. This just means rewrite from left to right the goal using both of these terms, basically.
Wait, so it applies, so rewrite applies add left first and then IH in this, like,
Yes, but it doesn't apply. It rewrites.
so it
Because apply
uses-
means something else.
okay, it uses add left first and then IH, so the order matters here. Could you switch?
I think so, yeah. It does a rewrite rule.
Yeah.
So actually, let's just try it. You don't have to believe me. Yeah, it does. It doesn't like it.
Yeah.
What if you add left after you rewrite with the
I don't think it should work. I think I'll try to do it in the right order.
probably,
Yeah, I think
yeah,
it needs to do that.
yeah.
Okay.
Cool, good questions. I think that's all. Any last questions so that, and then we're ready to do our first lean tutorial
Mhm.
is done. Maybe we can just, for curiosity, print the proof term. Okay, cool. And you see that it has the induction hypothesis and the two cases.
Mhm.
Let's see, let's explore it. Oh, okay, MPR is modus ponens in reverse. So it like, okay, cool. You can already like learn things about this. I wonder if we can do like equality, like check, heck. Okay. Okay, I'm just sort of like now you can inspect the proof terms basically, REFL.
Mhm.
Okay, you can see how equality is defined.
Oh.
Equality is defined if you can make this tuple, I guess. I don't know how else to say it. Like if you think about the diagonal of the Cartesian, that's how I think about it, or at least I think that's how I was taught in one of my logic classes. Let's see what other things exist. Yeah, so let's see, congruence. Okay, yeah, there's a bunch of things you can explore in the proof term to learn to understand it better. And the two things I've sort of discovered that are useful is to use Zulip for questions.
Mhm.
I like proof assists, stack exchange. There's also Moogle. It actually maps you to like the documentation or the GitHub, so that's useful. And the documentation,
Mhm.
I actually discovered that it's Google site search is better than search. So
Oh.
you search for whatever you want, but use Google site search, maybe because Google's job is to be a search engine. It searches this page better.
Wait.
I've just found it. So there's like 3 ways to search for things: Moogle search and Google site search. What else? You can also do exact question mark or rewrite question mark, like in tactic mode, and jump into the code. Zulip, Lean Prover Club here at Stanford. I think those are all the tips I have right now. And I'm in our doc, I'm making like smaller notes of how things work. Hopefully that helps us. Yeah.
Awesome.
You can also ask GPT-4, and it's not super good at it,
I don't think
honestly.
it does lean for it because it's
Yeah, it'll do weird things, but
very good things.
that's all I have. Any good?
Good, we're good. Thank you.
No worries. Let's see. How do we stop the recording?
Stop once you end the meeting.